So we've come up with the idea that we don't necessarily have to do all of these integrals in rectangular coordinates, and there are some subtleties when we go from rectangular to non-rectangular coordinates. And one of the issues, so let's just start at the beginning. So let's say we just want to describe points in 3D. We need three numbers. Like that's kind of what 3D means to a mathematician. And we could call them like Q1, Q2, Q3 or something like that. I'll fill this in a second. And different systems work differently for different symmetries. So for instance, if you have a charge that's spherically symmetric, maybe like spherical polar coordinates is good. So that's all in the art of you choosing the best coordinate for your liking, and you'll learn more and more as you go on. But we need three numbers, Q1, Q2, Q3. So technically we need more than just three numbers. So what else do I need from these three numbers or coordinate system? Okay, let me give you guys some coordinate systems that I think would be great because they'd be pretty easy to calculate stuff in. So I would like to keep track of the z coordinate as one of my numbers, z plus 1 as my second number, and z plus 2 as my third number. Would that work as like a good 3D coordinate system? Absolutely
No.
not. Yeah. What about x and y? Taking that feedback, and then x plus y. Would that be okay for a 3D coordinate system? No. So what is it that I need in addition to just a triplet of numbers? I really need a triplet of
Mutually
what type of
orthogonal.
numbers? Yeah. So orthogonal is actually like strong, and because we're physics, like we'll always be orthogonal. So the minimal thing you need is linearly independent. So what that means is QK cannot be expressed as a sum over all of the others. So there could be weights in front of them. The alphas are just numbers. But I can't make one coordinate out of any combination of the remaining ones. So there's got to be some piece of it that in some sense is distinct. So this is what linearly independent means. So clearly z is not linearly independent from z plus 1 or z plus 2, and clearly y plus x is not linearly independent from x and y, because we can make those other things out of the originals. We're going to go farther than that, and we're going to use not just linearly independent coordinates, but we're also going to use orthogonal coordinate systems in this class exclusively. And orthogonal coordinate systems, so let's say we have some Q1, Q2, Q3, is that at some point lines of constant Q1, Q2, or Q3 intersect at right angles. Which is the low budget way of saying they're orthogonal. Okay. So this is kind of trivially true for x, y, and z. So here's the line x equals 1, here's the line x equals 2. Pretend I can draw straight lines. X equals 3, and then here's the line, let's say we're in the fourth quadrant, we just never spend any time there. Let's call this line y equals minus 1, y equals minus 2, y equals minus 3. Okay. So everywhere that you plop down here, these things meet at a 90-degree angle. So what this also means is that x hat dot y hat equals what?
0.
Yes. So these are two ways of saying the exact same thing. And what this does is for other orthogonal coordinate systems, this generalizes. And this is worth me trying to draw the picture because maybe you didn't like 100% appreciate this. So this is for rectangular or Cartesian, depending on how you like talking about it. I will do my best to draw the same idea in spherical coordinates. So first I'll try to draw a perfect sphere. Just kidding, we can use the thing that's in. Let's do it again. So my three coordinates in spherical polar are r theta phi. So a line of constant r, or a surface of constant r, would be this entire sphere. And then now let's look at a surface of constant theta. So that is a line of constant latitude. So let's put it up here. So there's theta equals constant, r equals constant. And then we have phi is constant, so that would be a line of constant longitude. So we'll do that. So that's phi is constant. And if, as best as I'm able to draw this, you will notice the same two things are true. One is that the lines of constant latitude and longitude, if you, zoom in, you're a tiny little ant walking on the surface of the globe, those should intersect at a 90-degree angle. And the other thing that should be true is that r hat, theta hat, and phi hat should also be mutually perpendicular. So what these unit vectors mean is the direction in which I'm increasing. So theta hat would be the direction in which I'm increasing theta, which would be that. And then phi hat would be the direction in which I'm increasing longitude. So that would be, if we take like kind of the Greenwich mean convention, would be that direction, but it doesn't matter. The point is they intersected a 90-degree angle, and r hat is coming off of the surface itself. So again, these two things mean I'm in an orthogonal coordinate system. Is that phi hat dot r hat, for instance, equals 0, or these lines of constant r theta and phi intersect at 90-degree angles. And likewise, if you, maybe I'll leave it to you guys, you could draw the curves of constant coordinates for spherical cylindrical, cylindrical polar coordinates. So the curve of constant r or rho would be this infinite soup can itself. Can't draw an infinite soup can. And then a line of constant phi would be something that just etches one particular theta down the surface of it, and then a curve of constant z would intersect like this, and you can squint at them and see that their unit vectors are perpendicular and the lines themselves intersect at 90-degree angles. So, for instance, the plane of z equals constant intersects the soup can of rho equals constant at a 90-degree angle everywhere they intersect. So those are orthogonal coordinate systems. We're never going to leave them because, once you get non-orthogonal coordinate systems, the world gets very, very squirrely indeed. Okay, any questions about that? It's honestly just like a really long form definition. Okay, there are conversions in between these. And I'm going to put an asterisk by this because I'm going to draw a sort of cartoony version of this. And I'm going to put a caveat on it that maybe you'll see if you get into an analysis class, or actually it shows up in complex analysis. And it definitely shows up in general relativity, the idea of maps and atlases and stuff like that. I'm just going to say they're functions that convert in between them. So x is generically, for some other coordinate system, a function of q1, q2, q3. Y is generically a function of q1, q2, q3. And z generically is a function of q1, q2, q3. So you pick another coordinate system, and I should be able to convert back and forth in between that and a home coordinate system. So I could call this like q and sigma or something like that, but I'll just use x, y, z, and q. So likewise, q is a function of x, y, and z, dot, 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 because I think you get it at this point, and q3 is a function of x, y, z. Okay, so the caveat is that might need multiple functions. So famously, if you go from a polar coordinate to a flat coordinate, there's no single function that will let you do that because it's not one-to-one as you kind of project along the poles, but that's just kind of a cultural side note. And the way that you think about this in some sense is just like a single vector is like a real thing, but it has multiple coordinate decompositions. So if I have a function, or if I have physics that's actually living in 3D, it's got 1, 2, as many as you can dream up, possible different representations in terms of coordinate systems. Right? So the things that are true, and we've covered but are worth reminding ourselves of, are that are is really just if I want to express a vector, or unit vectors in particular, I got to remember that unit vectors themselves are unitless. So if I want to have something be meters, I've got to put that on the components themselves, right? And the way that might work in a Q basis, I guess, are I would have Q1, Q2, Q3, but each one of them, generically QK, are unitless themselves. So that means that if I choose to, for instance, describe a vector in some different coordinate system, v1 q1 hat plus v2 q2 hat plus v3 q3 hat, that these things have whatever physics units I need. And what should also be true is that A dot B should be the same in any coordinates. And I will write this, and then you guys will correct me. So the curl of two vectors, regardless of how I express them with, some other coordinate system. So at first we were just like making them manually, but now what we're going to do is talk about like explicitly vector fields in spherical polar or cylindrical polar, for instance. So what is the one thing I have to keep track of with a cross product in a different coordinate system?
Whether or not that coordinate system is right or left-handed. Exactly. It's going to maybe flip the orientation of the vector.
So same in any coordinate system up to an overall sign. And just like we're also going to keep it to keep it to orthogonal coordinate systems. We're also going to keep it to left-handed coordinate systems, but I just want you guys to realize, at some point you might get creative and make your own coordinate system, is that there are possibly left-handed ones out there. Okay, so that's all the fine print. So let's just, with one last reminder, get into all the stuff that basically we've covered so far, but I want to write down again before using it. Because we might have units themselves that have, for instance, units of radians or what have you. We got to keep track of scale factors now. And the scale factors might be like something weird and arbitrary for some coordinate system that you yourself dream up. So let's say I've got a line element of length, and that's dx I hat plus dy j hat plus dz k hat. This is notation. So for instance, d theta in spherical polar, this thing has units of meters in SI. We need meters, we can't do radians if we're going to add this to other differential elements. So for some generic coordinate system, we're going to use this notation, h1 dq1 q hat 1. h2 dq2 q hat 2. h3 dq3 q hat 3. So these HIs are the scale factors. And they're chosen in such a way that the units of H dq1 need to be length. So the scale factor itself might be 1. So for instance, for Cartesian coordinates, they're 1. But for other coordinate systems, we might have to choose something else. Okay. So as an example, so depending on the particular contour or surface, some of these terms might vanish. But 2 of these we can write generically. So the general formulas. For dl and d tau. And then we'll talk a little bit about d sigma. And while you're doing that, I'll just draw a cylinder. Okay, what's the line element, general line element for some curve in cylindrical coordinates? And we'll call the triplet of numbers we're keeping track of rho, phi, and z. So the first one we get for free because rho already has units length. So d rho rho hat. And then what about the phi component? What do I have to write here?
In order to get the length of the arc, you have to do rho sine phi times d phi.
So let me top view this. So if you're looking down at the top of a cylinder, so the difference in between the cylinder and the sphere is the cylinder is always flat. And so kind of like phrased the way that we talked about that sine theta in spherical polar coordinates, like everywhere is the equator. If I want to walk around a line of constant rho, that doesn't get easier or harder as I go up or down the cylinder. So everywhere where I go, this is rho, and this actual length in terms of coordinate space is d phi, but what's true about this trip around the edge?
It's rho d phi.
Rho d phi. Right, so it's the sphere because the sphere kind of bellies out at the equator where you have to worry about that projection, the sine part. So drawing it like that. So here's North Pole, here's South Pole. It's the sine part is, gets bigger and bigger as you get towards the equator. But because the cylinder doesn't have an equator, it's really just all of these are just rho d phi. Yeah, cylindrical might be the hardest because it's like easier than you think. So we have to use the arc length formula. We get rho d phi and then phi hat, and then dz is just dz. So dz z hat or k hat, depending on how you want to denote it. Okay, and then I would double check that units of length now, because radians times meters is meters, and then units of length. Okay. So what's true about a bit of volume for cylindrical coordinates? So for Cartesian coordinates, what I would do is I would just take all of these and multiply them together, dx times dy times dz. What's the analog of that for some random other curvilinear coordinate system? So I just got to product both the coordinates, differential coordinates, and the scale factors. And whoops, I see that I forgot a d there. Trying to write too fast. So in this case, I just multiply all of the things that showed up in front of the unit vector. So for the volume element, it's just d rho times rho d phi times dz. Volume elements don't have an orientation. We can rewrite this a little bit. So rho d phi dz, right? Non-vector. Okay, what's the problem with trying to write down one and only one expression for a surface element?
It depends on the actual surface that you have.
Totally, right. So I could have one that's pointing up like the top lid of a soup can, or I could have one that's pointing at the edge. So generically, we would just say that this is going to be, so this we can say actually, like HJ, they will probably look something like this. HJ, Q, DQK. Q hat, okay, cross A, oops, I went from K to J, what a mess. Okay, we'll use I. They're going to look something like this. So coordinate in one direction, cross product coordinate in another direction. where these two things are not equal, right? So the things that we have to do is make sure that it's got scale, it's got the right units, and that, you know, the cross product going from first coordinate to second, or second to third, or third to first will give us something that's oriented in the correct direction. But it does depend on the surface. Okay. So with that as a bit of a warm-up, I'll give you guys spherical polar and see if you can write down at least the two things that you can write down. So now, same exercise, but spherical polar. So what's the most general line element you can write down in spherical polar? And we'll call this r theta phi.
It would be dr in the r direction plus r d phi hat plus r sine phi d theta theta hat.
Yes, except either just in your brain or memory. Yeah, the usual convention is to call theta the second coordinate. Like you just said phi, but that's actually technically correct. It's just by convention, people usually call theta the azimuthal coordinate, or the co-longitude.
So
yeah,
theta being the one on the...
Exactly.
Yeah. Okay.
But you know, you can have your own personal coordinate system as long as it has some angle times r, and then exactly right, some angle. But now you have to take the sine of the other thing, d phi hat, right? And so this is something that, you know, we kind of went through a couple of times. The theta is always the same, so I have d theta, and I turn that into an actual distance by doing r d theta. But then the phi part, as I project down into the xy plane, it gets bigger and bigger as theta gets bigger. So that's r sine theta d phi for that. Again, d sigma, you got to work it out based on the actual thing that you see. And then d tau is, I just take the coordinates in themselves and multiply them together. And doing a little bit of rearranging, this should be r squared sine theta dr d theta d phi. So that is a volume element in spherical polar coordinates. Okay, but in general, what it should occur to you guys as true is that I don't have to do anything aside from just keep track of the scale factors, because all of these things are just scale factor times coordinate, scale factor times coordinate, and then product of all of them. So I can just say, like, look, scale factor for the r coordinate is 1, scale factor for the theta coordinate is r, scale factor for the phi coordinate is r sine theta. And these two things are a complete and sufficient description of the coordinate system. So you tell me it's an orthogonal coordinate system, and then you tell me the scale factors. Okay, that to some degree is a bit of a review. What we haven't done, we've used this in the context of integral calculus, just like, no, you need actual units of length if you're going to talk about an area or a length. We haven't talked about this in the context of differential calculus yet. And the gradient is easy, but that's it. I mean, honestly, the divergence and curl are easy, provided you just don't feel like proving the formulas. So let's say you want to do some differential calculus in curvilinear coordinates. So we've run into essentially the same problem is, just kind of start with note. So let's take a physics thing. So let's say that the position of a particle as a function of time is minus 1/2, well, call this y, I guess, y of t, minus 1/2 gt squared plus v naught t plus y naught. You guys remember that? And then I want to look at the velocity as a function of time. What do I do and what happens to its units? So what I want is dy dt, right? And if the units of this are meters, let's just talk about it in SI. The units of this are meters per second. And this isn't some quirk of just physics. This is kind of baked into the calculus itself. When you think about this as little piece of y, little piece of t, this is meters per second. And generally, if we have something, partial or total derivative, and I'll try to pick some things that, I don't know, psi. I have d psi by d nu. What are the units of that?
They'd be the units of psi over units of nu.
Exactly. So they'd be the psi units divided by the nu units, right? So this is a property of derivatives. So what I can't do is this, and you know it by just like looking at the units of these things. So what about the gradient? So let's say I ask, is this the gradient in spherical polar coordinates? I have some function f, and now I'm representing it in spherical polar. So it's f of r theta phi, and then grad f, question mark, is that equal to partial f partial r hat, plus partial f partial theta hat, plus partial f partial phi hat. Of course, you know the answer is no, but why not? What's wrong with this?
You're missing the scale factors for those coordinates.
Right. Okay. This proof, if you want to do it yourself, it is definitely like back of a napkin kind of proof. Just go back to single variable calculus, go back to the definition of the derivative, and then you see like the delta x in the bottom, limit delta f over delta x. You realize that scale factor in the limit, the thing goes to 0, just like the scale factor. And it shows up where? Upstairs or downstairs. So if we want to make units right, with the derivative, or if you think about where the coordinate shows up in the denominator, you realize that, okay, the correct form of just a derivative or the gradient, so it's also true for just like one plain old ordinary derivative, has to look like this. df dqk in some curvilinear coordinate system, we get a scale factor and it's got to be downstairs. Whoops, so let me write this. And this is a little bit of notation where sk has units length. So SKs are going to be the actual lengths. So for instance, DSK would be HK, DQK, right? Because ultimately we're going to have to add lengths to lengths. So the gradient is actually really easy. The gradient just says put a scale factor in the basement. So we can just jump right into maybe a hard sounding question. Okay. And when I give the triplet 2 pi over 2 minus pi, this is what left-handed means, is that I can't just kind of like make up order in which I give you the coordinates. It means that this really is our theta phi. And I'm never going to give, unless somebody's tells you, and I can never imagine a reason why they would want to do that. If you get a triplet of points in spherical polar coordinates, it is going to be r theta phi, which is basically presenting them in the correct right-hand rule direction. R hat cross theta hat should be equal to phi hat, and theta hat cross phi hat should be equal to r hat. And you should have enough to get this, so give you maybe 2 minutes. So first would be writing down what the gradient operator is in SPC, and then taking it and evaluating it. Okay, let's start by writing down what partly because I'm trying to like lead you guys into doing something funky. What is the gradient operator in spherical polar coordinates? So first term, just d by dr. And if I wanted to be a little bit pedantic about it, I would say it's 1 over 1. The scale factor for the r coordinate is 1. What about the next term in the gradient operator? So that is the, yeah.
1 over r.
Yep. So I have the scale factor 1 over r, and then d by d phi, and then the last one, the d by d theta. Now I'm doing it too. And then the last one, the d by d phi, would be its scale factor, so 1 over r sine theta. So just do that to this thing. So we have d by dr of alpha r squared sine theta r hat plus 1 over r d by d phi of alpha r squared sine theta theta hat. And then there's nothing in there that depends on phi, so we'll just say 0 phi hat. And this is grad f. And then grad f, we get 2 alpha r sine theta r hat plus 1 over r d by d phi, so we get alpha r squared cosine theta theta hat. And then we want to evaluate this at the point 2 pi over 2, I don't care, because there is no phi. So that becomes 4 times alpha times 2, sorry, 4 times alpha times 1. So it's 4 alpha r hat, and then 1 half, or is 2 alpha r squared, so that's 2 times 0, because cosine pi over 2 is 0. Okay, so if we want to maximize the ascent of this function, go in the direction that it's increasing the greatest, we would go in the radial direction, right? So just directly away from the origin. Okay, so you guys happy with that? I mean, so far, you know, differential calculus is easier than integral calculus, which is always the case. Okay, here is, and if you watch the recording beforehand, maybe you know what I'm about to try to do. Here's where, to some degree, the wheels fall off the bus. I have a gradient operator, and it's 1 over h1 d by dq1, 1 over h2 d by dq2 for some arbitrary curvilinear coordinate system, 1 over h3 d by dq3. And then I'm tempted to say that this is equal to 1 over h1 d by dq1 v1 plus dot dot dot. I mean, it's really not a lot of dot dot dotting, but it does save me a little bit of writing. And I'm tempted to say that this is true for a vector function. So we just took the gradient of a scalar function. And we haven't talked about vector fields yet. So I'm tempted to then say that this is true. Q1, Q2, Q3. 1 over h1 d by dq1, 1 over h2 d by dq2, 1 over h3 d by dq3, d1, v2, v3, right? Because we have del. I'm going to give you guys a function or two, maybe. So, and you can tell me if you think it's going to be curly. And you don't have to give me a number, just, you know, visualize it. And we'll do this in spherical polar because we've been talking about spherical polar. K phi hat. Okay. And what I really want is, you know, if you're good, you can give me positive or negative, but 0, non-zero. So do you think this function K phi hat should have a curl?
Probably not.
What does K phi hat look like? And my suggestion is look down from the positive z-axis.
Mm-hmm. It's just like, let me see, like a scalar pointing in the positive phi direction. So like, if like the phi angle like comes down from the z-axis, then it just points kind of like tangentially to, I'm imagining a unit sphere. So like length k tangent to the unit sphere on the z-axis.
Yeah, so actually on the z-axis it gets a little bit weird, but let's maybe take a step away. So we're like somewhere near the North Pole. The phi direction would be the direction that you're, by convention, it's counterclockwise. So this would be where V points here. Where does V point on the other side of the North Pole? Which is to say, which way does the angle phi increase?
The opposite direction.
Down. So V points there, and then V points there. I think drawing 8 of these would be better than just drawing 4. But you get something that looks like this. And then if I take another step, because K is constant, I would get something that looks like this. Okay, just based on what you know, like geometrically about, let's just, what I wanted you guys to do is look at this and give me the wrong answer. Hopefully I succeeded. Just based on what you know about curls in geometry, does this function look like it should have a curl, like a circulation? Yeah, and there are a whole bunch of ways now that we're kind of, intellectually armed to make that determination. One is that it really looks circulate-y. The other way is that if this was a force field, would it be conservative? Can you think of two paths from A to B, one that helps me and the other one that always, pushes back? I definitely see how if this was a force field, I could pick this path and I would have positive work and this path negative work. So everything about this says, the geometry itself says that this should not be equal to 0. Okay, this naive formula where we just took the del operator, which works well, it is correct for the gradient, and we just threw it in as the second line in the curl formula that we got from Cartesian coordinates, what would that tell me about the curl of this? Because really all that's going on here is with our naive formula, we would have that third line of 0, 0, k, a constant. So that would give me 0, even though, in the back of my mind, I'm like, I really don't actually think that this is a vanishing curl function. So this is like a really long form way of saying that these two kind of hopefully naive ways of using this, which is correct, are not right. And that the divergence and the curl in curvilinear coordinates are much more complicated than they might seem once you know the gradient operator. Okay, so really long form warning, like please do not use this outside of its scope of practice, which is for the gradient only. Okay, so what's really going on with this, and this is in the supplementary videos because the proofs just did the divergence formula and I think it's enough, is that why doesn't this work? So this is important to know. And you can see it on this picture. So this is where phi hat points, pretend these are unit vectors. So vector fields have two things that are changing. So for a vector field expressed in some curvilinear coordinate system, and this wasn't true in Cartesian. So first of all, the component functions themselves change. V1 is a function of Q1, Q2, Q3. That's not a problem. We can deal with that. But what else changes as I go from two things, technically, as I go from point to point to point. So the QK themselves also change. And in this case, what looks, because of a coordinate pathology, what looks like a constant function, so this is just, what do we call it, K phi hat? These are constant symbols. But what's implicitly true about phi hat? Phi hat itself is changing. Right? And that is not what's showing up in this formula or this formula. This is why they're wrong. because these things themselves are changing, right? Okay, so what you have to do is you have to appeal to the basic geometric definitions of divergence and curl as like the limit as volume goes to 0 of surface integral over d volume. I'll leave that, deriving that on this whiteboard would be tough. It's worth looking at them, at least letting it kind of wash over you like a Wagner opera. One, to remember that you can't use these naive formulas, and secondly, to get some more practice thinking about multivariable calculus and multivariable Taylor's theorem. So for us today here, I will say proofs happen. And I will write down their general curvilinear coordinate manifestations, and then we'll just use them until we run out of time. Okay, so proofs happen, and what we have is the curvilinear divergence formula. And it looks like this. I've got a vector field. It's expressed in some curvilinear coordinate system. Out front, I have the determinant of the Jacobian. And then I have d by dq1, v1, h2, h3, and you'll be able to see the pattern really quickly. And I'll write it in such a way that you can see the pattern really quickly. So there are other ways of writing this where you put like all the components, the v's out front, but I like this because when you look at the indices, you kind of see what's going on. Okay, and really glibly what's going on is the fact that the scale factor shows up because the Q's don't have, these are coordinates, they don't have the correct units. That's outside. And then inside the scale factors show up because the components and the unit vectors themselves could be moving. So I could have a function that, you know, symbolically kind of looks like it's constant, but what's really happening is the unit vectors themselves are moving all over the place, right? That's what happened with our curl. And then we have a curvilinear curl formula. And our curvilinear curl formula looks really wild. I will say there are other ways of writing this. So you might see something that maybe on the face of it looks different, but it, I don't know, maybe you found some really disreputable mathematical resource online, but they should be the same. So there are some lightly different ways of repackaging the scale factors. I like this one because it leaves the derivatives alone, and it's hard enough writing all the derivative stuff. Okay, so they're not just taking the thing that was our del in curvilinear coordinates and then just slapping it in as the middle line of the curl, for instance. Okay, so let's do this as a good, straightforward first example. So we decided that the vector function k phi hat, obviously it's in spherical polar coordinates, so writing this is redundant in spherical polar coordinates. Should have a curl, even though our naive wrong formula said it shouldn't. We can now calculate it. So calculate the spherical polar coordinate curl for that function, just constant phi hat. And it's kind of annoying. I am pretty sure that this will win. You will never spend as much time as you're about to taking the derivative of a constant function. But the point is that the k is constant, but the phi hats swirl all over the place. And that's really what you're keeping track of. So I'll give you guys 2 minutes to do that, and then we'll do divergence in whichever coordinate system you guys want. Okay, so we've got this function, constant phi hat, and we want to compute the curl. If we did it with kind of the naive formula, we wouldn't get it right. So let's just continue on this line. What are the scale factors for spherical polar coordinates? Like if you can just multiply them all together and give me the denominator of this whole thing, that would be great, all in one shot.
That r squared sine theta.
R squared sine theta is exactly right, right? So this is basically the scale factor on the volume element, if you recognize it from that. And then we have r hat times 1, so that's the scale factor from radial coordinate. And then theta hat times scale factor from the theta coordinate, so that's r. And then phi hat times r sine theta. And then d by dr, d by d theta, I'll use the abbreviated terminology or notation. And then here we have 1 times nothing, so it's 0. And then 1 times nothing because there's no phi hat component of the function. And then we just have, aha, here's the magic, h3, so that's r sine theta times k. So kr sine theta. Okay, and then it proceeds with just normal determinant-y stuff. Okay, so for the first part, yeah, we get something in the r hat direction, and then we should also get a term in the theta hat direction, and then no term in the phi hat direction. Somebody happy with their answer for the curl? So after cleaning it up a bit, well, so we write it out in 2 steps. So yeah, we still have this thing out in front. So the 1 over r squared sine theta. And then what I should get is kr cosine theta from that derivative, the theta part. And then that's in the r hat direction. And then I should get a minus, and then kr sine theta in the theta hat. So we lose an r from the derivative, but then we get it back from the thing multiplying the unit vector. And then we can clean that up, and we can get k over r cotangent r minus theta. Okay, and then, you know, up until 5 minutes ago, if you were talking to somebody who said, I took the derivative of a constant function and I got a cotangent, you would say, I've never met somebody worse at calculus than you, but this is correct. So this is really something that's going on. And there's something worth pointing out. So anybody know what cotangent does at theta equals 0 and what that means with respect to our function, which really isn't a real physics function. So there's something really spooky going on with that thing. So first of all, what's cotangent of 0?
It's undefined.
Yeah, so we got a 1 divided by 0 error. What's going on at theta equals 0? What point of the sphere am I at? So I am right at the North Pole. And this function doesn't care if I'm at the North Pole. It says, no, 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 I always have constant vectors pointed in the phi direction. So there's this blow up because I basically have an infinitely curly function. If you look down at the North Pole, there's a function of constant, or a vector of constant length pointing in each one of these directions. And that's true as you get to theta equals 0 itself. So the reason it's undefined is because there's like an infinite curl, because I have two vectors pointing in opposite directions, for instance, at the same point. That's a really, really, really strong swirling drain. Okay. So any questions about that? Okay, we'll do your guys' choice. We should do a coordinate divergence formula. I could give you one in spherical polar, or I could do one in polar cylindrical. Up to you guys. Want to do an analog of this particular problem, but in cylindrical instead, or in or spherical polar? So the cylindrical one actually is, maybe we'll save that because there's something kind of crazy that goes on where the divergence that you don't think should vanish vanishes, and you'll talk about that a lot in E&M. So let's just let me give you a basically the same sort of thing, but in but for divergence instead of curl. So we'll present it in the following way. So let me have a vector function, r theta phi, and we'll call it k r hat. What do you think about the divergence of this function? Should it be 0 or non-zero? To first visualize the function.
Non-zero?
Yeah, so this looks like a really divergency thing, right? So these are constant arrows bristling out from the origin. Literally everywhere you go, there's an arrow of the same length and it's pushing you away from the origin. So, you know, with our kind of heuristic about divergence being the spread of a vector field, this looks like it should have a divergence. So geometrically, this should have a divergence. We'll just say looks divergency. And divergency isn't a real word, but whatever. Okay, again, same thing has happened with us with the curl, is that because this is just constant times r hat, if you use the naive formula where you just take the coordinate derivatives and then throw a 1 over scale factor in front of it, this would vanish. So you have to use this formula if you want to correctly determine the divergence. And this is an example, like geometrically, where you see that's the case, where our bad formula that we just kind of guessed at would totally give us the wrong answer. It would say that this thing vanishes. So this is the correct divergence formula. Give you guys, should be pretty quick, maybe like 2 minutes to apply it to that, because it's only got an r hat component, which is kind of nice. And then in the last 2 minutes, go over the answer. Do this. I have a vector field in spherical polar coordinates, and I want to compute its divergence. I'll write down everything just really quickly, although obviously a lot of these terms are going to drop. Okay, I have this thing, which now you're probably really familiar with, is the product of the scale factors, or the thing that multiplies the volume element, and that's r squared sine theta, as it was before. First coordinate is r, so we have d by dr, v1 h2 h3. So it turns out that is what saves us. v1, that's the radial coordinate, or radial component, so that's just k. And then the second two scale factors, notice these all have the form is some vector component and then the other two scale factors. So this is k times r squared sine theta. So h2 is r and h3 is r sine theta. Plus d by d phi. This has no phi component, the vector field itself. So that's 0 times 1. That's the scale factor for the radial coordinate, h1, and then r sine theta. And then d by d phi, just for completeness, 1 times r times 0. And obviously, because of the zeros, these are both gone, but I just wanted to write them, so we had some practice with them. Okay, so we have the divergence of this vector function is r squared, 1 over r squared sine theta. And then d by dr of this, so that's 2kr sine theta. And then we get some cancellation, so we get 2k, and the thetas are gone. So we have 2k over r. Okay, now the last question is, do I believe this? Yeah, I think the divergence should be the same regardless of whether or not, it should be irrelevant as to what theta or phi we're at. So this vector field is rotationally invariant, so our answer should be rotationally invariant. The only thing that matters is how far away from the origin we are. And if you think about it, we're really far away from the origin, and these vector fields are going to kind of end up starting to look parallel. So they're really divergency when they're all bristling away from the point 0, 0, 0. But as you get out towards infinity, they're basically going to look parallel, so the divergence is going to disappear. So I kind of like that answer. And I like the fact that we shouldn't have any theta or phi dependence, because if I rotate this vector field in theta or phi, it looks exactly the same. Okay. So that's something that if we use the wrong formula would have vanished. We use the correct formula, we get something that seems generally sensible. So on Thursday, we'll do more practice, and there's some more practice with this on the homework. But that's the basics. I mean, really just those two wacky formulas for curvilinear derivative calculus. And starting on Thursday, we'll go into Fourier series and transforms. Okay. As always, I'll hang around for a bit after class. People have questions, but otherwise I'll see you guys on Thursday.